I'll start by asking if there are any questions from yesterday. You came and asked me some questions. I will address one or two of those, but if there are more questions, please ask. So one question that was asked to me was that the last bit of the central thermal support of the fuel exhausted core was not very clear. So I did go through it a little bit quickly. So I will redo that bit. So we had a star where a little bit at the center is the core, and you have a surrounding nuclear burning portion, which is the shell. And this core, it doesn't have nuclear burning, so there is not much heat flux out of the core, so the core is practically isothermal. So let's say the core mass is mc, radius is rc, temperature is Tc. So the pressure at the surface is Pc. And the rest of the mass, which is most of the mass of the star, is in the envelope, which ends in this shell burning, in the burning shell. So at the base of the envelope, let's say pressure is Pe, temperature is Te, and the mass of the envelope is m. So you need to have both mechanical and thermal equilibrium. If the core is supported by thermal pressure, then you will have Te equal to Pc, Te equal to Tc. Once these conditions are satisfied, the core can actually remain stable even though it is not generating nuclear energy. So to look at this equilibrium condition, what we did was to use the stellar virial theorem, where we had 4 pi r cubed. So now it's rc cubed Pc is you have gravitational energy and twice the thermal energy. The gravitational energy is minus g, there will be some constant, g mc squared over rc. And then there is another constant, which now gives the thermal energy, which is simply proportional to mc times Tc. Total mass times the temperature. So that's the condition for the core. So this will then give you Pc equal to some constant. Actually, this is not minus, this is plus. Sorry. So you have minus some constant C1 times, absorb all the constants in C1, mc squared over rc to the power of 4 plus some constant C2 times mc Tc over rc cubed. If you plot this, then Pc as a function of rc will go through a maximum. And let this maximum be Pc max. one can get that maximum by differentiating this expression and then finding the value of RC, substituting back that value of RC into PC, and then you will get a number. I will leave that algebra to you. PC max is some C3 times TC to the power of 4 by MC squared. In order for there being an equilibrium between the envelope and the core, the envelope pressure has to be somewhere there. At least it has to be below PC max, so that you have an intersection between the two, and that gives you a balance. So this then gives us the condition PE must be less than or equal to PC max. Now PE, it is like the full star. We have seen before the central pressure at the star can be written as some 1C3, another constant C4 times TE to the power of 4 by M squared. This is less than or equal to then this quantity C3 TC to the power of 4 by MC squared. So this will then give me the condition for thermal stability of the core as, T is equal to Tc. So I have MC by M less than or equal to some square root of C3 over C4. And now one can put in whatever coefficients were there in C3 and C4. So this is roughly equal to, if you evaluate it, it will be roughly equal to 0.37 mu envelope over mu core squared. So which means the core mass cannot exceed this amount. If the core mass exceeds this amount, then thermal support in that environment is not possible. The core is going to quickly contract. But until this point, even though the core is not generating thermal energy, nuclear energy, it can remain stable because of the energy generation surrounding it by the shell. So this limit actually has a name. It's called Schoenberg. And it is actually due to this condition that in the core collapse of a massive star, you can get compact objects like neutron stars of various different masses, and you can also get direct formation of a black hole if you have a very massive initial star. Can you make that connection? Why that is so? If there was no such limit, or rather if the limit was much smaller, if, for example, the thermal balance of a massive core was not possible, then actually we will not have black holes forming directly in the core collapse of a massive star. So there is a direct relationship between there being a mass which, although inert, is supported by the thermal environment of its surroundings. And that being a significant fraction of the total mass of the star. So the connection goes as follows. So let us say I have, at the end stage of stellar evolution, where the core has exhausted all nuclear burning stages, and basically made of iron now, so therefore, even though you compress it and heat it, no further nuclear energy generation is possible. So in that case, imagine what is going to happen. So you have a stellar core. It is, of course, it's iron core, which will be surrounded by a silicon burning shell, which will be surrounded by an oxygen burning shell, which will be surrounded by carbon, surrounded by helium, surrounded by hydrogen. So you'll have a whole hierarchy of shells around it. That's not particularly important. What is important is that, let's say you are growing the iron core from a small amount of mass. The silicon shell which burns around it produces more iron. It is going to add to the core. The core is not generating nuclear energy. So if it were to find support, it has to be only degeneracy pressure support. Right? So the core is going to become like a white dwarf. So that white dwarf, sort of white dwarf analog, is now being held by degeneracy pressure. It's made of iron. And given that iron has a charge number of 26 and mass number of 56, so it's got more neutrons than protons. So the mu E, amount of atomic mass units per electron, is a little bit more than 2. The upper mass limit, the Chandrasekhar limit equivalent for mu E appropriate for iron, is not 1.4 solar mass, but it is somewhat like 1.1, 1.2 solar mass. So as more ash gets added to the core, the core mass is going to increase. And once you get to this mass limit of about 1.1, 1.2 solar mass, what's going to happen? You're going to get a collapse, basically, right? So once it collapses, then depending on what other equation of state intervenes at high density, you will get in this case, you will get a neutron star. And the gravitational energy that is released, it will come out in various forms. It will come out as a shock wave, it will come out as neutrinos, which is going to expel the rest of the envelope. Now you can see that no matter what the initial mass of the star was, this is going to be the final fate, as long as the star has completed nuclear burning all the way to iron, right? Because finally you are restricted to the core mass growing up to the Chandrasekhar limit of that particular composition. And this happens to be iron, so therefore it will always be like that. So we'll actually never form a black hole this way. As soon as you get to 1.2, it will just collapse and eventually form a neutron star. But what this tells you is that if the star is massive enough, if the remaining envelope of the star is massive enough, remember the star has evolved through many stages of nuclear burning to come here, and every time it goes through core nuclear exhaustion and then shell burning and so on, the star goes through a giant phase and then some matter is expelled. So eventually, when you get to this final stage, the star's original mass has been reduced significantly. But whatever mass remains, if that is large enough, then this MC, which is held by thermal pressure before degeneracy needs to intervene, can be larger than 1.2 solar mass. It could be larger than, considerably larger than 1.2 solar mass. It could be larger than 2 solar mass. It could be larger than 3 solar mass, depending on how much envelope matter is present. So that thermally supported core will collapse only when the PC max, as you add mass to the core, the PC max is going to go down because PC max is proportional to 1 by mc square. More and more matter added to the core is going to reduce this. So eventually, it is going to collapse. But now it is going to collapse at a point where it has not only exceeded the degeneracy pressure support limit, it has even more mass than that. So all of that is going to collapse. So now you're going to get an object which is not just this 1.2 solar mass, which was collapsing, but it could be any larger mass depending on what the initial mass of the star was. So you can have 3 solar mass collapsing, you can have 5 solar mass collapsing. Of course, when you have then the shock wave that will come out from the core, it will expel some of it. But the total mass that will remain in the compact object can significantly exceed that 1.2 solar mass that you would have otherwise got. And that is how, in direct collapse, you can form heavier neutron stars and you can also form black holes. If the total mass that remains in the final compact object exceeds the maximum mass of the neutron star, then you will directly form a black hole. So this limit actually plays a very key role in deciding what kind of compact object will remain at the end of massive star collapse. Are there other questions that I would like to you want me to answer? I mean, all of this is decided by the equation of state of the matter that is currently present, right? So here it is mostly thermal equation of state. When I said that this is going to be held by degeneracy pressure, then you use electron degenerate equation of state. And then when you're trying to see what is going to happen after the collapse, what is the final property of the compact star that remains, that's going to depend on its own equation of state. So at every stage, equation of state is involved. It depends on which equation of state. No other questions? Okay, so then I'll move forward from here. So today, I am going to address the question of equation of state as you raised in the context of neutron stars. So if the mass of the core that finally forms the compact object after collapse happens to be within a range which is small enough for nuclear matter to support itself, then you will get a neutron star. So the neutron star is a star for which the hydrostatic balance you can compute in non-rotating case using the TOV equation, which we did in the tutorial yesterday. And the property of the neutron star will, of course, depend on the equation of state. It is not to say that different neutron stars will have different equations of state. Equation of state is an open problem because we actually don't know exactly what the equation of state is at very high density. And this is related to a fundamental physics. What is the nature of the force when you bring two nucleons very close to each other is still not fully determined. We cannot determine it in terrestrial experiments. We cannot determine it theoretically completely either. So this is an open area of fundamental physics where astrophysical constraints from the measurement of neutron stars is as important as doing accelerator experiments, measuring nuclear properties, or even doing theoretical modeling of nuclear forces. So let's go through a few properties of what the nuclear equation of state, what we know about nuclear equation of state, and what it is likely to be, and where the uncertainties exist. So neutron stars are called neutron stars because they are made of neutrons. Can the neutron star be made entirely of neutrons? Can't hear you. No, why? Why can't I have just a pure collection of neutrons? And we have already seen that neutrons can produce what's called a degeneracy pressure, right? So neutron degeneracy is certainly an important component of the pressure that contributes to holding up a neutron star. But you're saying that you cannot have a pure neutron star. In 1932, when Landau proposed that there could be a neutron star, he was thinking of a pure neutron star. Why do you think that is not possible? Neutrons can undergo beta decay, correct. So if you leave a neutron in free space, then it will undergo beta decay, produce a proton and an electron, and the decay time scale is about 11 minutes or so, right? So if you have a pure collection of neutrons, What is preventing those neutrons from decaying into protons and electrons? Is there anything that can prevent them? No. Beta decay is going to happen. And then let us say that protons and electrons that are produced, now we are talking about a gravitationally confined system, they remain within the system. Right? It's not as though you produce protons and electrons leave the system. You also produce neutrinos, and neutrinos can leave the system. But I will ignore that for the moment. So you start with, let us say, a collection of pure neutrons, and by neutrons begin to decay. They start producing protons and electrons. And then what's going to happen? Eventually, will all neutrons decay into protons and electrons? Why should degeneracy pressure drop the whole process? Degeneracy of what? No, you started with some occupied state. Now you're going to reduce the number of neutrons because they're going into protons and electrons. So freeing up states for neutrons. But you also have electrons. So equal number of electrons. So charges get screened. I mean, the sun is made up of basically hydrogen. It's 25% helium, you can ignore it. But it's basically electrons and ions, right? So you have a large blob of electrons and ions where the Coulomb repulsion is not really playing any role. It's the thermal forces, thermal pressure, which is acting as gravity. Degeneracy is important. You are right. But it is not the degeneracy of the neutrons. Neutron Fermi energy is going to reduce as more and more neutrons convert themselves to protons and electrons. But something rises. What will rise? The Fermi energy of protons, Fermi energy of electrons are going to rise, right? So you will then reach an equilibrium. So you have neutron going to proton plus electron. Actually, I will write this. So these reactions, both reactions can occur. So this is our well-known beta decay. And this is inverse beta decay. So the system is going to find a balance. The balance will occur when the chemical potential balances on both sides of both equations. Nu and nu bar leaves the system, so their chemical potential does not matter. I have ignored the presence of muons, but we'll not worry about that for now. So how am I going to write mu p? First of all, let us consider stars where so I'm not going to worry about thermal energies at all. So how will I write these three terms in this expression? Yesterday we did the expression for Fermi momentum, right? So at a given density, I can always compute Fermi momentum for any species, right? So what do I mean by Fermi momentum? That means if I now want to add another particle to the system, that particle must have a minimum of that momentum. All states below that are occupied. So that means it will have that amount of that energy associated with that momentum is the minimum energy you need to add particle to the system. And that in fact is the meaning of a chemical potential. How much energy do you need to add one more particle to the system, right? So this is nothing but then the Fermi energies of these particles. And when this is satisfied, you say the system is in beta equilibrium. Note that the Fermi momentum of protons and Fermi momentum of electrons will be equal, because the Fermi momentum depends only on the number density, and because of charge neutrality, you will have equal number of protons and electrons per unit volume. So these two Fermi momenta are equal. But of course, the Fermi energies are not equal, because the energy also includes the rest mass. Now, as you start, let us say, from a hypothetical mixture of full neutrons and no protons and electrons, and then let neutrons decay and fill the volumes with protons and electrons, the Fermi energy of protons and electrons begin to rise. They were zero, or rather just the rest mass to start with, and then they're going to rise as more and more particles populate the system. As they rise, at some point, you would find that the electron Fermi energy has become comparable to or larger than the proton-neutron mass difference. Now, in free space, we only see this occur and not this. Why is that? And why does neutron decay into proton and electron? Because the rest energy is larger, right? So you will get a lower rest energy on the right-hand side. So reaction proceeds that way. And that mass difference between neutron and proton is about 1 million electron volts, 1 MeV, right? Proton is about 938 MeV, neutron is about 939 MeV. So now, if you have this attempting to occur in a situation where there are electrons present with Fermi energy larger than neutron-proton mass difference. Is this reaction going to occur? Suppose it produces the proton on the right-hand side. It also needs to produce the electron. And that electron needs to be placed on top of the Fermi sea. For that, a minimum amount of energy is required, which is the mu E, which is the Fermi energy. And if that energy happens to be larger than the amount of energy you will gain by going from neutron to proton, there is no space to place the resulting electron. So, if such a thing happens, then you are going to stop this beta decay. But then, if this really energy is so high, then the inverse beta decay is going to occur, and some of these proton-electron pairs will actually spontaneously convert to neutron until a balance like this is restored. So you have traffic both ways, and the system is in equilibrium. So this therefore requires that electron Fermi energy rises to a level which is comparable to the proton-electron mass difference. Remember, what we are talking about here is neutrons also in a situation where Fermi energy of neutrons is not zero. So the mu n, the energy corresponding to the neutron there, is not just the rest mass of the neutron, but also the corresponding Fermi energy. So if you keep making it more and more dense, the neutrons will also gain more energy. So there is more energy to spend to populate electrons on the right-hand side. So therefore, this is really a dynamical equilibrium depending on density. You will get different ratios of proton to neutrons depending on what the density, local density is. And that one can solve for. In fact, this equation can be solved for to give you the proton fraction x. And you will find as you take density to very large values, if this is the only thing that is happening, then it will tend to a number like 1/8. So that is the large density limit of proton fraction. And if you have time in the tutorials, maybe you can try to solve this. You can actually do this as a homework. You can discuss this in the tutorial. Just write all these Fermi momenta in terms of density, and then take the density ratio of protons to total. You should be able to get 1/8. All right. So that is only about 12% of the total number of baryons. So rest of the baryons, let's say 88% of the baryons, and almost 90% of the baryons will be neutrons. So the name neutron star is still well deserved, although you cannot have pure neutrons. Right? So this mixture of neutrons, protons, electrons is the material that is now going to exert pressure to hold itself against gravity. To be able to see or to be able to construct the density profile of a neutron star, you would then need to know what is the relation between pressure and density in this material. That is the equational state of this material. The equational state of this material is actually fairly well known up to a density which is roughly equal to the nuclear saturation density, which is the density that is obtained inside an atomic nucleus, which is pretty high anyway. What is the density inside an atomic nucleus? If you want to express it in grams per cubic centimeter or any unit of your choice. Anyone has a number? You have to also state the unit. 10 to the power of? 10 to the power of 17 grams per centimeter cube. Are you sure? Yeah. Let's make a quick estimate. What is the number of atomic mass units? Take any nucleus. Take any reasonable nucleus which has both neutrons and protons. What is the lightest nucleus I can think of? Both neutrons and protons. Let's take helium. 2 neutrons, 2 protons. What is the number of atomic mass units? 4, right? Okay. So 4 atomic mass units. And what is the size of a nucleus typically? 10 to the power of minus 15 meters, right? No. Which is a femtometer. That symbol FM also nicely coincides with what physicists have termed it. 10 to the power of minus 13 centimeters is a Fermi, right? A Fermi is a femtometer. So 10 to the power minus 13 centimeters, so this is 10 to the power minus 39 centimeter cubed. And you have 10 to the power minus 24 grams. So the density is roughly about 10 to the power 15 grams per cubic centimeter. The nuclear saturation density is typically given as, let's call it NS, 0.15 baryons per Fermi cube, which is roughly about 2.5 times 10 to the power 14 grams per centimeter cube. It's an important number to remember because most activity of neutron stars will be in reference to this density. So you did the TOV solution yesterday. started with a high central density, and then did everybody get the solution, at least for one star? At least you would have seen that at the surface the pressure falls to 0, so the density falls to 0. So the star itself is going to start from a very low density at the surface. So where material is more or less normal. Since you have started with iron, so you probably have a thin outer crust made up of regular iron, very at the top of the layer. If some material has been deposited on it from either the mantle or from accretion from other things, then the top surface can have also lighter elements. But very quickly, as you start going inside, the density is going to rise rapidly. This you can easily see in the TOV solution that you have done yesterday, that very quickly the density begins to rise. And as the density begins to rise, the beta equilibrium composition of matter is going to become more and more neutron rich. Remember, at the surface, you have normal nuclei. In the normal nuclei have roughly equal number of protons and neutrons. Not exactly, but roughly equal numbers of protons and neutrons. A little bit more neutrons than protons. And that's simply because protons have charge, so therefore there is a Coulomb energy that enters in the total energy of the system. So having more neutrons is more favorable when the Coulomb repulsion becomes important. So if this you may have seen many times, if you take the number of neutrons versus number of protons in nuclei, and let's say this is the equality line, then the known terrestrial equilibrium nuclei, the stable nuclei, they follow this line and then go up somewhat like that. Roughly n is about 1.5 times z towards the upper end. So this is the line of stable isotopes, but you can also create isotopes, and other isotopes exist, which need not be infinitely stable, but they are at least possible to create, and they're stable for a while. So there is a stability island of nuclei. So that stability island goes something like that. This side is narrower than this side. And then there are some preferred values of n and z, which we call magic numbers, where nuclei are extra stable. So in the beta equilibrated neutron matter. At the surface, you start somewhere here, where the nuclei are very similar to what you would get in terrestrial context. But as you go to higher and higher densities, you begin to get nuclei which are on the left side of this distribution. So you get nuclei over here, you get nuclei over there. You preferentially get nuclei at the magic numbers of magic number of neutrons, though you might get a few in between. These are neutron-rich nuclei. So these are chemical species which you would not normally encounter in terrestrial conditions. Now I have drawn this stability line to the left of this stability line. If you pack more neutrons in a nucleus, the nucleus cannot hold it. So this is called neutron drip line. And on this side, you have proton drip. So as you move to more and more neutron-rich environment, you can see that you are diving into situations where you are actually going into neutron drip. So as you look at the run of density from the surface of this neutron star to the interior, at some point you will find the neutrons that exist cannot be completely confined within nuclei. So you then have a coexistence of nuclei like this and free neutrons. So that's called the neutron drip point. So if I look at a section of the neutron star, I have an outer portion where we have neutrons and protons in the mix, but all neutrons and protons are held inside nuclei. And these nuclei are not like the terrestrial nuclei, but they have larger fraction of neutrons in them than the terrestrial nuclei. But this can only occur up to a certain depth. So this, I would say, is a region where you have nuclei. Now will come a region where you have nuclei plus free neutrons. Okay, this is called the neutron drip region. The boundary is roughly at 4.3 times 10 to the power of 11 grams per cc. This is the neutron drip. As you go to higher and higher density, the fraction of neutrons in nuclei keep dropping. There's a more and more fraction of neutrons that begin to appear in the free sea. Eventually, there will be a boundary where all nuclei will disappear. You'll only have free neutrons, free protons, and free electrons. So this is roughly at nuclear saturation density. So here, no nuclei. So in the neutron star literature, this region is called the crust, and this is the core. And off the crust, this part will be called the outer crust, where no free neutrons are present, and this is the inner crust. And later on, at higher densities, you now have a mixture of neutron, protons, electrons with no nuclei present. So it is clear that the composition of the material changes drastically from the surface going to the interior. An equation of state, after all, depends not only on the basic constituents, but the composition itself. So you will not be able to make one single equation of state based on just one description of the composition to describe the whole neutron star. So you have regions where you have to treat the interactions differently, and there are other regions where different treatment has to be done to get the interactions. So people have approached this piecemeal, looking at what are the primary forces that are responsible for generating pressure at different regions. And this whole crustal region has a fairly well-defined equation of state. The problem occurs in the interior. Yeah. So this the distribution of this material as a function of radius is going to depend on the spin. The structure, when you solve it, then you have to take into account the rotational energy as well. But for a given density, the state of matter, that is more or less independent of spin. So that is not something that would depend on the overall spin of the object. So now let us ask, what is the real problem with the equation of state? We have started by saying that when you have neutrons, neutron degeneracy provides pressure, and why is that not an adequate description of neutron star equation of state? After all, for a white dwarf, we had electrons which were degenerate, and there were other species also. Of course, there are protons, there are neutrons as well, the nuclei are there. Yet, the degeneracy pressure of the electrons served as an adequate description of the equation of state. Of course, small corrections like Coulomb corrections and so on can be done, which will make some changes. But by and large, the electron degeneracy pressure gave you a good approximation to the structure of a white dwarf. Why can't we do that for the neutron star? What do you think is the main bottleneck? Okay, so how do we know that it is not being supported only by degeneracy pressure? So we can compute the structure of a configuration which is supported only by neutron degeneracy pressure and then see what we get. So that is one part of the tutorial problem which you may deal with. So if you only have neutron degeneracy, then the maximum mass possible mass of a neutron star is roughly equal to .7 solar mass. This was actually calculated by Oppenheimer and Volkoff in 1939. Right? So this is Oppenheimer-Volkoff limit. In stellar astrophysical situation, can we generate neutron stars of mass less than this conveniently? You need to go through the full evolution of the central core. And we know if the central core ends its evolution at a mass less than about 1.4 times the mass of the sun, then it's already going to be held by electron degeneracy pressure. There is no further contraction that is going to take place. So you're going to get a white dwarf. But you're not going to get a neutron star from a standard stellar evolution, which is going to be in mass as low as 0.7 solar mass. So this actually does not describe the objects that we're looking at. But then why do objects of higher mass exist? And that is obviously because neutron degeneracy is only partly responsible for providing the pressure. The bulk of the pressure comes from nucleon-nucleon interaction. The nucleon-nucleon interaction which is a strong interaction. If you plot the potential, you can have something of the form which is called a Reed potential, which as you come close, the potential becomes more and more negative, so that means the force is attractive. The strong interaction is attractive, not a very long distance because it's a short range force, but it's attractive at longer distances. Then there's a branch which becomes repulsive at short distances. And this occurs at a distance of roughly about 1 Fermi or less. So when you take these nucleons, the nucleons are not interaction free. This neutron degeneracy pressure that we have talked about is for a non-interacting gas. In an interacting gas, you have to put in the interaction potential as well, find the total force. So what this tells you is that if the density is a little bit lower in that region, the net pressure is going to be less than the degeneracy pressure because of the attraction between nucleons. And when you squeeze them to densities where the interparticle separation is a Fermi or less, then the net pressure is going to be larger because there is now a repulsion between particles. So this modification is necessary to describe the equation of state of the neutron star. If this repulsive branch did not exist, we would not have neutron stars of the masses that we see today. The problem, though, is that the nature of this repulsive force has not yet been determined well, either by experiment or by theory. So this very high density branch of nuclear interactions is still an open fundamental physics question. You would ask, why can't we do this in accelerators? In accelerators are built to probe interactions at very close distance, right? The higher the energy that you raise the particles up, the smaller is the de Broglie wavelength, and therefore the shorter is the distance you can probe. So why can't we do this by just having an accelerator with a higher and higher energy? Anyway, we are building them. The problem is that that is never going to address this problem, because you are creating this short distance probe by raising the energy of the particle, means that whenever you actually have a signal, you have a collision at high energy. As a result, the matter becomes very hot. So neutron star requires, the description of a neutron star requires the equation of state which is very cold and very dense. You can get to small separations in the terrestrial accelerators, but at very high temperatures, because when you collide, the temperatures are much higher than Fermi energy. So this cold equation of state is, so far we have no laboratory method of probing the cold equation of state and measuring things for that matter. However, we have a theory which has been proven correct by many, many measurements, right? So the theory of strong interactions, QCD. So why can't we just solve it from QCD? Consider if this was the electromagnetic force. No matter what arbitrary condition I can conjure up, I can always then try to solve that by writing an appropriate action and then looking at what the forces will be. Why are we having such difficulty for this case? Why can't we just take QCD and compute it? What do you think is the source of this problem? So how do we compute forces of interaction or energy of interaction between two particles from a field theory? QCD is a field theory. So is electromagnetism. So what steps would you follow to describe or evaluate energy density, let's say, or energy per particle in a given field theory? But that's a macroscopic thing, right? How do you know the values to put in the stress energy transfer? So that's assuming that you have a appropriate Lagrangian which you can write. It's got a V term. So you only need to know what the V term is. Yeah, so you need to start at a microscopic level. So in a field theory, what you will do is you will write propagators. So you take Feynman diagrams and you say, okay, two particle interaction. And then integrate over all possible orientations, all possible energies, momentum vector of the exchange boson. And then, so you have two vertices, then you go to next order, have multiple vertices and so on. And you have to sum all those diagrams. So this is perturbative QCD. So, and this is normally the way we know how to do things. So in this perturbative QCD or in the perturbative field theory, you will sum all these diagrams and then contribution of all these diagrams, and then you'll find an effective force. This is nice and converging in case of electrodynamics, for example, or even in case of weak interaction. Because the coupling constant which we'll have to apply at each vertex is a small number. In case of electromagnetism, it is fine structure constant, which is 1 by 137. In case of weak interaction, it is something even lower. So if we try to do this for strong interaction, then the coupling constant is roughly equal to 1 at about 1 GeV. Then it drops as you go to higher energies or higher densities, the coupling constant drops. But so let's say around 100 GeV, the coupling constant is about 0.1. If you go to extremely high density, the coupling constant vanishes. So that's called asymptotic freedom in QCD. So if you go to extremely high density, the quarks themselves are not, they don't feel any force between themselves, they're free. But as soon as you come to realistic densities where we want to work, the coupling constants are too high, so the series never converges. So we don't have a theoretical approach to really deal with this. Not so far, at least. So it then boils down to making guesses. So every neutron star equation of state that we have today are based on guesses. You have some measurements. You have some constraints on the equation of state from laboratory measurements of nuclear properties, as well as some other measurements which may come from astrophysics. Based on those few constraints, you then try to extrapolate the known nature of the force to regions which are not yet explored. And obviously, any such extrapolation is model dependent. So it will depend on what form of a function that you are going to use to explore. And typically there are two different approaches which are taken. One is doing a mean field theory approach. The other is this microscopic extrapolation. From nuclear data. As I said, up to the saturation density, we more or less know the equation of state well. It's only when you go above the saturation density, then we start getting into these problems. And this has produced a whole family of equations of state. And that is something that one is trying to grapple with. Which is the correct equation of state? Which is therefore the correct expression for force between two nucleons at very short distance? And clearly, since all of these give you different equations of state, each member of this equation of state family can be used to construct a mass-radius relation of the star. You have tried doing mass-radius relation of neutron stars using TOV equation for a particular equation of state. You change the equation of state, the mass-radius relation will be different. So, so you will have in different equations of state mass-radius relations which look different. And have also something which goes like that. This makes it possible to probe this by astrophysical means. There are multiple astrophysical observed quantities which you can bring into play. First, measurements of mass themselves. Suppose I prove the existence of a neutron star, which is a firmly well-measured mass of this value. Clearly, the extrapolation that produced these equations of state do not match that observation. So therefore, we can rule out those equations of state. So just the mass measurements alone can distinguish between some families of equations of state. Now, if we are able to measure mass and the radius of a neutron star simultaneously, that is an even more constraining observation. So we may be able to tell between this equation of state and that equation of state. It's not that we have actually achieved that goal so far very well yet, but that is certainly a direction where neutron star astrophysics is striving to go. It is not only mass and radius. You can also compute other quantities based on these same models. One of them is moment of inertia. A moment of inertia can be measured in a system, for example, when you have a binary where you have strong gravitational force between two neutron stars, and the angular momentum not being all aligned will cause the angular momentum of one of the neutron stars to precess. And the rate of that precession depends on the moment of inertia. So from the measurement of the precession rate, you can constrain the moment of inertia. And at the same time, if you have the measurement of mass, for example, of the system, and that again acts as one of the important observational constraints. Yet another thing that we can do, thanks now to gravitational waves, is to probe the deformability of a neutron star, tidal deformability. When two neutron stars are about to coalesce with each other, each neutron star is subjected to a tidal force due to the other one. The tidal force is nothing but the gradient of the gravitational force times the size of the object. So that means one end of the object is being subjected to a larger gravitational force than the other end. So as a result, the object is stretched out. Depending on the forces that act within the neutron star, clearly the amount by which it will be stretched out will be different. So every equation of state gives you a measure of tidal deformability. And from the shape of the waveform in the gravitational wave neutron star merger, you can actually constrain the tidal deformability. So that brings in another constraint on the equation of state. We will look at also constraints that come from, let's say, thermonuclear X-ray bursts, which occur on the surface of neutron stars when I talk about some phenomena in binary systems. So one of the key emphasis on neutron star astrophysics is because of the ability to try to constrain equations of state. And all of these different methods are coming together to gradually improving the astrophysical constraints. So I think I will stop here today. We'll have 5 minutes left, so I can take some questions. Yeah. No, so how do we define equation of state? Equation of state is just a relation between pressure and density, right? So if it is just a relation between pressure and density, then we do not expect the equation of state to be different for different neutron stars, right? Because it's a more fundamental property of the gas, or fundamental property of the material that makes these two neutron stars. You may have different masses. That will give you different solutions of TOV equation with the same equation of state. So to start with, we at the moment do not make a distinction between the equations of state of two different neutron stars. It is not to say that there cannot be any difference, because there could be some difference in composition or some difference in the way the neutron star is formed can cause some differences, but perhaps those differences will be quite minor. But let's say one family of neutron stars, which we call neutron stars, I drew particularly this mass-radius relation. This type of mass-radius relation comes from strange matter, strange quark stars, SQM, where the composition is not neutrons, but it is fully made out of quarks. And these quarks then are basically asymptotically free inside. They're held together by gravity. And because of their kinetic energy, they have a pressure. And so these strange quark matter stars will actually have different equation of state compared to a neutron star. So suppose we don't know that the strange quark matter stars exist actually. So far there is no evidence that they really exist in nature. But suppose you found yourself in a binary system of a neutron star and a strange quark matter star, then when they merge, their equations of state are really going to be significantly different. But I think that is a scenario which probably has not many adherents at the moment. No, so it depends on how you have constructed the equation of state. If particularly for neutron stars, if you have constructed it from some microscopic theory, you have actually first computed these different components and then added them up. So you can go to the microscopic theory and that will tell you. But if you are doing this from actual measurements, then there is no direct way of decomposing it. You will then have to again resort to some theory of matter to figure out what these different components are. So to just state here, so all these theories can be used to produce this quantity, the energy per baryon as a function of number of baryon per unit volume. And from this you can compute everything. You can compute pressure is NB squared times del EB del NB. You can compute density, which is NB EB over C squared. And you can also compute chemical potential if you plot EB versus 1 over NB. And let's say it's a curve like that. Then you take whichever NB you want, and you draw a tangent. The slope here is pressure, and the intercept is chemical potential. So all of these theories of measurements and extrapolations, what they're trying to get is this fundamental quantity of energy per baryon as a function of number density of baryons.
Any other questions? Okay, going once, going twice, going thrice. Thank you, Dipankar.
Thank you.
So we come back at 11:30.